Okay, hello everybody. So it's a great pleasure to introduce today's speaker. So much so that I couldn't cede this to anyone else, and I had to do this myself. So Professor Bill Dorland was born and grew up in Arkansas in Texas. And then went to the University of Texas, so he comes from a distinctly non-vegetarian background, in more ways than one.
I have a gun in my bag.
So, after Texas, he went on to graduate school at Princeton, where he did a PhD in plasma physics. But at the same time, concurrently, did a master's degree in the Science and Society. What did you say, Bill?
International Scientific Affairs.
International Scientific Affairs. So this is you see that his interest in politics and society as well as science goes way back. He did this at Princeton's famous, but as we now learn, politically incorrectly named Woodrow Wilson School. And so he knows what he's talking about, both when he's talking about public policy and science. So when he was at Princeton and subsequently when he went back to Texas as a researcher at the Institute for Fusion Science in Austin, he was one of the very first people who worked on developing properly quantitative modeling frameworks for predicting performance of fusion machines. And in fact, in the mid-90s, Bill and his PhD advisor Greg Hammett and some PhD students of Greg's made quite a big splash and quite a big impact on the World Fusion Program by producing the first systematic predictions of the performance of the International Thermonuclear Reactor, which was then designed. And in fact, the ITER had to be redesigned as a result of some of this, which is a rare thing, that a theoretician goes beyond conceptual insights and wades into actually telling people how to build something. He went on. He went from Texas to the University of Maryland. Bill and his collaborators were amongst the very first people who developed the fully self-consistent ab initio kinetic modeling frameworks for tokamaks, and he and his people are responsible for what to this day remains essentially a definitive paradigm for how the turbulence in tokamaks is structured. From Maryland, he moved to Imperial College, London, in 2001, where I first met him. And this was at the time this was part of a sort of a D-Day style American invasion of British plasma physics, which was led by Steve Cowley. Who is sitting here somewhere? Yeah, he's over there. Steve was the general, Bill was chief of staff, and I was infantry.
First at the page.
That's and survive. Bill moved on to become a professor of physics at the University of Maryland. After this, where he was also promptly appointed director of the Honors College of the University of Maryland. So this is a college within the University of Maryland, which is for students who are particularly clever.
It's like Merton.
Particularly, you have just stolen the joke that I didn't tell him, but we think alike. So yes, it is like Merton College. It's a special place within the University of Maryland. So he's mentored many students over this period at Maryland, some of whom are in the audience. In fact, one of them flew in from Sweden to see Bill. So you see, he commands loyalty amongst these people. And this is not accidental. He's been very much an inspiration to everybody who's worked with him. And that's partly why he has been such a frequent visitor in Oxford, and specifically at Merton College. I believe he stayed at Merton College every time he visited Oxford, and he's visited Oxford every year for the last several years. So the way this works is whenever we, in the plasma group at the Parles Center, get sort of stale and complacent and run out of ideas and so on, we fly in Bill to inject vitality and a sense of urgency into us and sort us out, and he does. So on this occasion, he's very fortunately agreed to apply the magic touch to the Merton physics community as well, and so it's a great pleasure. I give you the 21st Ockham lecturer, who is Professor Bill Dorland, and he will talk about nuclear forensics.
Thank you, sir. Okay, so the way I've structured this is for the folks up front. And I want you to engage with me. I've done it as I've got breaks where I want to hear from you and what you think. Anybody else can participate as well. And if they're undergraduates, in fact, hiding in the back, also can participate, no problem. And this topic is one that I got interested in when, as Alex said, I was interested in science and public policy, and I worked on areas of international aspects of civilian nuclear reactor safety, because it was relatively soon after the Chernobyl accident, and there were a lot of policy and scientific and technical issues that came up that people hadn't quite thought through all the way. And this topic is not that. This is a different topic. Nuclear forensics is the question, well, we'll engage with it in a moment, but it's fundamentally the question of, so in the US, if I were talking about this, I would talk about a show we call CSI. Do you have that here? Yeah. Okay. So, crime scene forensics is when you try to figure out from a little piece of hair or a little bit of dirt who did it and why. And in the TV shows, it always works out within 43 minutes that everything can be figured out. In fact, nuclear forensics is attempting to answer similar questions. If someone were to detonate a nuclear device in a city, whether in America, in Britain, in Pakistan, anywhere, how would we figure out what had happened and who did it? And the set of issues that are raised are interesting and intertwined between physics and non-physics issues. So I want to talk about those. If you're here and you're not a physicist, I think there are still plenty of questions to engage with. In fact, I've left out equations and left out detailed decay chains and fission pathways and things because I want you to focus on the parts that are reasonably general and will stand the test of time instead of being perhaps technologically made obsolete. Okay, so given that, this slide is taken from a paper in 2010, and this is a material called Trinitite. Does anybody want to venture a guess what Trinitite is? There's a hint in the, let's go here. Oh, and by the way, when I lecture at the University of Maryland, you don't have to raise your hand. Just holler out.
I think it's something that was performed during the first atomic bomb test at Trinity in New Mexico.
Right, so the bomb test was called Trinity. There wasn't a place called Trinity, right? And the desert floor under the device was about a 10 kiloton, if I remember correctly, atomic bomb. The sand on the desert floor was glassified and turned into a new mineral, a novel mineral that didn't exist before, called Trinitite. And for 50 years or 70 years, people left it there. You could occasionally go to a rock and gem show and someone would have a tiny sample and you could buy it, and it's basically safe. And it's don't eat it, okay? Like that. stick it in your ear. But there wasn't a lot of thought, at least in the, oh, and by the way, this is an unclassified in every possible way because I do not have clearances. I haven't studied this as a classified person, so this is an open talk. So I may say things that aren't true, but that's out of ignorance. Maybe there are classified versions that are different. So to the classified world, people didn't go back and look at this Trinitite to see what they could learn from the explosion, because after all, they knew exactly what they'd exploded. They knew exactly what time, they knew exactly everything about it. And what was interesting is recently, this is a paper from 2010, technologists went back, gathered up some of the Trinitite, did these kinds of detailed microscopic of various kinds assays to try to see whether they could tell any information about the Trinity device from the glass that was made as a result of the Trinity explosion. And that's an interesting question because that's the kind of question that we'd like to be able to answer should something be detonated in one of our cities. We'd like to be able to look at what's left, look at the debris, and be able to say something. And this is a terrific opportunity for that. And so this is in the Proceedings of the National Academy. It's an eminent journal. And I'm not going to say too much more, except that the work I did as a part of a panel, the other members of the panel were all experts in this. There were 3 directors of the weapons labs in the United States. There were all manner of people who knew this material inside and out. But we were doing an unclassified report. At the same time, there was a classified report. I'm going to tell you what we learned in the unclassified report. And it was published, I think, in around 2008. All the advances that are described in this paper were from 2010, and there have been other advances. And so I don't mean to tell you that I'm telling you, the absolute latest and greatest. I'm telling you what I learned a few years ago. And as I say, I'm going to stick to the things that are likely still to be compelling and true. Okay? Okay. So with that introduction, there are a few concepts that we have to talk about and agree on so that we don't get confused about what the problems are. And in fact, one of the reasons that this study was undertaken was precisely to disambiguate these terms and to try to get to a point where if the day came when we needed to talk about this topic, there would be some clarity about what was being said and no kind of obfuscation on purpose or otherwise about what was known and could be known. So the very first topic is the difference between interdicted or intercepted materials versus post-detonation debris. And you can imagine that it is a completely different forensics challenge to try to figure out where something came from. If you caught somebody and they have it in their backpack, and it's got hairs and fingerprints and other kinds of identifying or potentially identifying signatures, versus you're looking at the debris of a major city where everything's been sort of splattered all over the place, right? It doesn't mean, and I'm going to focus on the latter, the post-detonation forensics challenge. It does not mean the other one is not important, and in fact, so I have a picture here. This is a picture from a port somewhere in the world, and this device and this device, every container that is driven out of that port goes through this gate, and this gate is designed to look for signatures of something unpleasant in that container. And they might be looking for neutrons or looking for gamma rays or something, but they're looking for signatures of devices that might be quite dangerous to be out and about. This is absolutely sweeping the world. Many, many, many ports and border crossings around the world have this kind of technology. And now that you know what it looks like, if you're out and about, you can see them. They're just sitting there. It's rapidly evolving technology, which is one of the reasons I don't want to talk about it. Today, it has a very high false positive rate. Why would they have a high false positive rate? So again, we'll start up front and then anybody can chime in. Why would they design a system that 200 times out of 201 gives you the wrong answer?
Better to be safe than sorry.
Better to be safe than sorry, precisely. And you're looking for, you're better to be safe than sorry, and you're looking for perhaps a very well shielded device, right? Maybe they've encased it in lead in their container, whatever it is. And so, better to be safe than sorry means that 10 to 20,000 times that the trucks have been stopped and inspected, only 50 to 100 times has anything at all been found inside the container. Well, 50 to 100 stops is great if you're worried about the fate of your city. But if you're trying to run a port and you're trying to keep the flow of traffic through, that many false alarms is quite challenging. So while this is a technology that is ubiquitous and growing and spreading, it's rapidly evolving. And one of the things I wanted to say is there are many interesting careers in this broad area. So if you have an idea as a physicist of how you could improve the accuracy without sacrificing the number of correct finds, then this could be worth quite a lot. This is a very large industry now all over the world, and it could be very interesting to think about. What are some ways, not thinking about the technology too hard, what are some ways that you could improve on this that I've already hinted at? Can anybody think of anything? Again, I'm going to try to engage you a lot in question and answer.
Could you put some sort of detector within the containers themselves?
Okay, so this is getting at this is exactly in the direction, and then I can think of a tilt slightly away. So more detectors, perhaps in all the containers. Right. What could you do in slightly different than that even? Where are these detectors currently? They're either in his containers or they're at all ports. What else might you do? Anybody?
Put it on the boat.
Put it on the boat. Where else?
Integration times.
Freeways.
Freeways. Now we're getting there. How about everywhere? If you have them everywhere, you try to enter London by road or rail, and you have to go buy one of these things. Maybe the accumulated information allows you to know something. Maybe you could change the parameters of your search by assuming you're going to not just look once when it comes into the country, but maybe 50 times as it moves around the country.
Can you see them from space?
There are signals, so I'm going to try to stay away from details. There are signals which people look at from space, and I'll show you some examples of that. You can shield to the point where some of the satellite technology for always watching gets less important for traffic and more important for other things which we'll come to. I had an idea, which, not to get off the topic, but I was so thrilled by seeing something that somebody had done that I want to give you guys an idea. I challenged a group of students back at the University of Maryland to come up with, if everybody now has been tricked into buying an accelerometer on their cell phone, by actually giving them a smartphone to go along with it, what could you do with this accelerometer that would help change the world? And it turns out some scientists at Berkeley have already answered that question. And what they've done is they take everybody's cell phone and monitor the accelerometer, everybody that agrees to it, and they look for correlations in the signal. And if they find that everybody, now they're from Berkeley, right? So what are they worried about? Say what?
Earthquake.
Precisely, they're worried about earthquakes. So if everybody starts moving with the same frequency in highly correlated ways, then they can say it's an earthquake. And it turns out having ubiquitous earthquake sensing technology in everybody's cell phone is already saving lives. Because if everybody has this app and everybody agrees to turn it on, then you can get a warning on your cell phone of an impending earthquake wave coming in your direction before there's time for any other sort of back and forth kind of communication to go on. So that's pretty cool, right? I think that's just fabulous. And they've been deployed mainly around the Pacific Rim so that people, maybe the communication networks aren't as widely developed. So my thought was, if you guys could come up with a way, every smartphone also has a CCD, a charge-coupled device, part of your camera that can see all kinds of interesting signals besides visible light. Wouldn't it be interesting if you could have not just a few thousand ports watched, but instead you had millions and millions and millions of people doing the work for you and looking for maybe much, much fainter, harder to see, but maybe you could do something. So you guys do that, and if it works, you'll make a lot of money. Okay. So this is the problem of interception, and the problem of post-destination is really a completely different problem. So this is an image we'll come back to later. This is some American city in Ohio. And there was a study done assuming that some terrorists got their hands on a 10 kiloton device, meaning it would have roughly the same explosive power as the bomb that was dropped on Hiroshima. And they smuggled it into, in this case, an American city, and detonated it at ground level, and then what would we do? What would ensue? And it's an interesting question, in part. One of the things I learned from listening to the people on this committee and talking to people who've been thinking about this for years is it turns out the majority of senior members of government in the United States in roughly 2002 had predicted in 1992, that by 2002 there would probably be such an event in the United States. Probably. Above 51%. Above 50%. Now why would they have said that? What happened that would lead them to believe that? Test your history.
Fall of the Soviet Union.
Very good. Fall of the Soviet Union had just happened. There were concerns that there were relatively unguarded devices in large numbers out there somewhere. And the fear was that these things would find their way in the hands of all kinds of different motivated people into an American city. And so this report, it's called the Day After Report, you can find it on the web, was a group of people convened to say, what would happen? And what are the issues? And the things that they came up with that I wanted to highlight here for a moment in the post-detonation world. First, really key analyses need to be unclassified. So why would that be? Can anybody think of a good reason why, if you've got a great idea for figuring out something very important about this device that just exploded using some really clever physics, why would it be better for that to be unclassified than classified?
You can have more people working on the problem.
You can have more people work on the problem, and now carry that one more step. Which people working on the problem?
Well, potentially anybody. Like NASA's using people just to find, transits and stuff like that.
Right. So you get this large number of people engaged, and in particular, the thing I want to carry forward from that is people in other countries. And so if this happens in the United States, and the government in the United States says, we have an analysis which we can't tell you about, we can't tell you how we did it, but we know that it was London that did this to us. You'd like to know, before the next step, how they do, right? And so you would like to have access to all the same decision information to the greatest extent possible. And so there's a kind of understanding that dawned since the Cold War, from the 40s through the end of the 60s further. There was a great deal of what's called national technical means. Countries who were nuclear weapon states developed the technology to figure out what just happened in their own tests, to figure out what the potential adversaries had just tested. There was a lot of understanding, and it's all siloed in the countries. So I keep track of what I can know, and it's best that I don't reveal any of that to anybody else because I want to know it, right? It's kind of changing if we have non-state actors potentially doing this to us. You'd like to be able to get consensus internationally. So that was one thing that came out of their response. The second, obviously, if you think back to some of the terrible things that have happened in your lifetimes, people want to know who, what, when, why, how, immediately. But in this case, the pace cannot be frantic. And why would that be?
Danger of misinformation.
Danger of misinformation. So, yep, what else? Any technical reasons? What would set the pace? What kinds of things? Wanting to get it right.
That's what the decay chain.
Right, the decay chains proceed as they do, and to figure out what maybe was before, you have to wait until you have enough isotopic differences in the samples that you have to tell something definite. So there's some things that can't be done quickly, and I'll tell you a little more about timescales and what can be known when, regardless of instrumentation and everything else, because there's certain processes which are rate limiting. And then, this question of who is involved is not to say who did it to us. It's the question of who would help answer these questions. And this turned out to be the dominant concern of the committee that looked at this question in the United States. Because, the police of this city and the fire trucks, the first responders in the city would be in a unique position to get some information very quickly. And perhaps the FBI or the Department of Homeland Security or whatever you call the same things over here would be a national a response that maybe would take a little bit longer because they have to come from some central place. And then perhaps the Army or whoever it is in your country that has control of these devices could come in with a different set of information and concerns. And then, you see, there's so many potential parties who have concerns with this that it became clear that should this terrible thing happen, the coordination problems under the pressure would be excruciating and would be actually as difficult to solve, if not more so. So you could say we could do everything technically and still fail completely to understand in a timely manner, whatever that time is, and we'll talk about that, what just happened and how. So these are the things they came up with in their report. Given this set of interests, this set of questions and others that we'll talk about, why did I even mention the interception? Well, interception is somehow happening all the time, and it kind of gives you an idea of whether this is a made-up threat to line the pockets of people who would like to think about this problem, or whether maybe there's something to it. And this timeline comes from open information from the International Atomic Energy Agency, and these are intercepts between 1992 and 2006 around the world of various kinds of special nuclear materials, fissile materials. So there's highly enriched uranium. 100 grams was found here. 1.5 kilograms was intercepted by the authorities here. 1.8 kilograms, 3 kilograms. 400 grams of plutonium. That's very hard to come by unless you have a pretty serious intent. And, this is quite a lot of activity going on in the world. And this is just what I could find on the web. So I think and this actually is from a talk given at Imperial from a friend of mine, but the idea that there's something to think about, I think, comes from this figure, which shows that there's quite a lot of traffic in special nuclear material or fissile material that indicates that we've got something to think about here, and we'd best be prepared to the extent that we can. Okay. So this slide is not my slide. It comes from this fellow here. But I thought it was a good slide for just kind of once and for all establishing the various stages and parts of the problem. So reading the boxes from left to right, somebody wants to do something, that's the intent. They start planning it. The only ways to get at that are perhaps with intelligence, is it MI6 that's the James Bond? Is that right? Or is it MI5? I get confused on these numbers.
It's MI5 once they cross the border.
So MI6, fine, let's assume. And then maybe they acquire a fully operational weapon, or maybe just the special nuclear materials. They have to get it where they want to put it. They have to, maybe this is getting it across the world. This is delivering it to the target, and then there's an event. And I'm leaving my slides with Alex so that everybody can kind of look at all these things. There are many different problems along the way, each of which have different technical challenges, different political challenges, and it's just too much in one talk to talk about them all. But if you want to reflect on this family of questions, this is a great slide for kind of giving you a roadmap of what all's involved. I'm going to be talking over here about the event and immediately after. And so some of that is down here. We'd like to attribute, and I'll come back to that word, that's a very important word. We have to figure out how to respond to the event. And the first question is, what just happened? You know, was that a nuclear event? Was that a dirty bomb? What was it? And then, what does that mean for first responders and for people living in the area? So there's a lot of questions that happen after the event. Okay, so back to this, we're done with number one. I'm not going to say much about number two, except to say that there are three distinct kinds of scenarios that really have completely different technological and policy implications. The first is a dirty bomb. This is probably the most likely thing that will happen in our lifetimes because the amount of medical radioactive isotopes used to treat cancer and other things is very large. There's a lot of it. You know, every hospital to zeroth order has some. And it's very well guarded, but it's not very well guarded. And you could imagine going to lots of hospitals and getting a little bit of it and stuffing it all into a can with some dynamite. And when that exploded, you could imagine, that's called a dirty bomb, you could imagine that would have a great deal of fear, that would instill a great deal of fear in the population because people would be talking about radiation. So that's one kind of event. Another is a fizzle. That has to be the next most possible thing. If somebody wishes to do this kind of damage and they actually try to produce their own nuclear weapon, or perhaps they've stolen one or acquired one from someone else but they don't necessarily know how to work it properly. Maybe they have an explosion which is terrible but not equivalent of many thousands or tens of thousands of tons of dynamite. Maybe it's just a bad explosion, but it now has plutonium and other things perhaps. So that would be a fizzle. And then finally a full-scale nuclear detonation. And this is the one that I will be talking about. So forensic analysis, so I'm not going to talk about dirty bombs and fizzles. If you want to ask questions, we can. But I'm going to focus on what happens if there's a bigger problem. So the forensic analysis, as a term of art, nuclear forensics determines, these are a set of tools and technologies that allow you to determine the composition of the materials that were used, the physical condition, their age, provenance, where they came from, and the history of the materials. This is very important information that you could then pull together to paint a picture, perhaps, of how this came to be. Okay, so that's nuclear forensics. Together with the information from intelligence and law enforcement, nuclear forensics can perhaps most likely exclude some part of the story and say, well, it didn't happen this way, it didn't happen that way, but perhaps also tell you positive information about what just happened. So nuclear forensics is kind of the technical side. And the difference between forensics analysis and attribution is the thing that led many of us to undertake this report. The question of attribution is the question of who did it. Who did this to me? Who did this? And if I could tell you, in fact, let me ask you, what is, and Alex may disagree, and that's a hint, what is the most likely, if I said there will be an event, unfortunately, in a city somewhere, and we do the nuclear forensics analysis, and we determine where the device was constructed. What's the answer?
North Korea.
North Korea, he says. What else? Russia. Any more?
America.
America. So, of those three, let's narrow it down further. Why America, North Korea, and Russia? I could tell you a target, and maybe then we could narrow it down, but let's not do that. Where do you think it is? Which of the three? There's one that's far more likely than the others.
It's probably Russia, but bear in mind that the US has recorded haven't they recorded many warheads as being just lost over the years?
Yes.
They dropped
Yes.
planes into the Atlantic Ocean, so there's
Yeah,
at the bottom of the sea.
there's some at the bottom of the sea. There was one dropped on North Carolina or something. There was one dropped on Spain. You know, bygones. But the most that were intact, that probably were at risk, and we can talk about the degree to which maybe they were unguarded or not, the fear in the community is that it would be Russian, and that so the whole forensics thing tells you nothing in that instance. But you know, if you go in with a prior expecting that you might find it's a Russian device, and then you find it's a Russian device, you've learned nothing about who did it, right? You've learned nothing about who did it. The question of forensics and technical gets you nowhere in figuring out who did it, and the attribution question is who did it and possibly why. Okay, and attribution is the question that the politicians are going to want to know. And one of the reasons we engaged in this report was to outline what you could know from technical means versus what you would like to know, and then trying to keep the lines uncrossed before the pressure gets on to come up with an answer. And to come up with an answer in a time frame, perhaps, that's not even possible. So this disambiguation of 3 and 4 was the part that was most interesting to me. Now the timeline, I love Jay's statement, the timeline is screaming panic if it were to happen, right? Everybody would want to know yesterday everything about it. And as we'll talk about, there are timescales imposed by the physics that are going to say, you know, there's certain things you're not going to figure out, at least from technical means. And attribution is, you know, again, the difference between who did it versus what happened. Okay. So these 3 scenarios, let's just go over them very quickly. The dirty bomb I've already talked about. It has relatively few casualties. It's expensive to clean up because now there's radiation in, you know, in Leicester Square or whatever. And this is a terrible thing, but there's relatively few people actually injured or killed by such an event compared to these others. The Fizzle is a nuclear device that fails to work. That's next most likely. There are forensic opportunities there, but I'm not going to talk about those. And then the nuclear explosion is the one that we're going to focus on, and it's also the greatest forensic challenge. So why, from simple principles, would the forensics challenge for a nuclear explosion be harder than a Fizzle?
Because there's nothing left of the initial device.
Precisely. Yeah, all of the chemical and perhaps the box that was in, all of these things are gone, and there's perhaps no way to get any of that information back. To give you an example of how severe the forensics challenge can be, back on that chart there was a famous, I'll put it up, the Bulgarian. Can anyone see the Bulgarian? I think it's right here, right in the middle. This Bulgarian interception had many countries were given access to the material that was intercepted, and all these countries used similar tests and studied these things carefully, and they all came up with their best understanding of who done it, and they all disagreed. And this was with the benefit of any ancillary information that you could not get after it had been exploded. So the forensics challenges are great even if you have an intact sample. Okay, so this day after report didn't actually, different cities get targeted in these reports. In this case, they're targeting Washington, D.C. So there is the White House right there, and the Capitol buildings over here. And the idea is what I was saying before, there would be a ground burst with typical weather conditions, no warning, so the population is wherever they work in here. And what the basic finding was that 50% of the population in this red circle would suffer immediate major injuries or fatalities. And then the fallout, if the wind were blowing in that direction, 10 to 50% of the people in here would receive non-fatal injuries in the first day, and that star is my house. So this is a bit personal. So looking at this terrible consequences of something like this, the first overwhelming conclusion from anyone who looks at this problem is to prevent this from happening in the first place. And in my abstract, I challenge you to think about that. And so I want to take a second and you guys to tell me what you came up with. What strategies might exist for preventing us from ever getting to this point? Did you think about that?
Surveillance.
Surveillance, yeah. So let's count surveillance in the ubiquitous sensing idea. So keeping an eye out, okay, that's one stage and important. What else can you do? Yeah.
Make everyone think we've solved the problem of attribution.
Very good. That's right. So convince all your adversaries that you can determine with 100% accuracy that you finger them and respond.
So you're undermining this now.
I am undermining that accuracy. Yes. Nevertheless, it's a strategy.
Some of them won't care though, right?
Some of them won't care, which is why you might as well undermine it. What else? So, game theory gives you some ways to think about these problems. And I have the fortune to work with a fellow who got a Nobel Prize in thinking about these problems for his life. And he was an advisor to presidents going way back. His name's Tom Schelling. And when he comes into my class on this topic and challenges the students, he asks them two questions, and one of them is let me ask you, and we'll take a second, everybody can talk to your neighbor, see if you can come up with the answer, okay? It's contrived, perhaps, but you'll see the point. So you and an adversary are on the top of a very tall skyscraper, on the roof, and your legs are chained together. And the rules of the game are that if you can convince your adversary to give up, then you'll be unchained and he'll be heaved over. Or maybe he'll just be, maybe you can, let's make it easier. You'll just be unchained. Okay, so how do you convince your adversary to give up? See what strategies you can come up with.
What is he giving up?
Just give in. Let you win.
To what? Winning what?
What? To not be the one that gave up.
Given that.
No, it's contrived. It's contrived.
Okay.
These guys have already got close. I've already got Has anybody up front seen the movie Dr. Strangelove or How I Learned to Love the Bomb? This movie was came into Kubrick's mind after talking to Schelling about this question.
So it's a doomsday machine.
Yeah. So what's the doomsday version of it here?
If you jump, I jump, or something like that.
Let's flesh it out. You jump, I jump, but the other guys say, well, I'm not jumping.
Board to destroy that. I mean, in the film.
No, let's do it. You're on the roof.
We'll jump, chain together, unless you give up.
And how do you convince someone that you would be so idiotic?
Invade Iraq.
Invade
Iraq.
There's no time to invade Iraq. So
you have to automate it in some way.
What?
You have to automate it in some way so it's not an act of your volition.
Okay, he wants to automate it. That's a good point. So how would you, anybody come up anymore? So Schelling's answer was, you have to dance irrationally as close to the edge as possible, convincing the other person that you'll go over and take both. There's nothing that'll happen at any moment, that it's outside, it's a done deal.
So you elect Donald Trump.
Another solution which there's no time for. So that's a game theory kind of approach that says act like you're the most irrational actor in the room. And so this is the kind of thinking that one can engage. So now Here we have something terrible that we don't want to happen, and I've given you some hints as to what the most likely pathway that we could get to this outcome. And there are some strategies that you haven't said yet. You've got some good ones, but if we assume that there were some unguarded nuclear weapons in Russia, and they were, let's just assume they were stolen, what do you do? What do you do right now?
Build your own.
Say again?
Build your own.
Build your own, okay, to scare them off.
Yeah.
Yeah, okay. We'll get to deterrence at the very end, right? And so I was introducing game theory not to lead you to that question, but rather to just think about it, sort of abstract way. So, think about it some more then, and we'll come back to it. It comes up in about 3 slides.
Do you know these people who've stolen the weapons?
We do not know the people who've stolen the weapons.
Do we know what they believe?
We don't know
Can we
what they
threaten them
believe.
with anything?
The best strategy means we don't need to know who they are, what they believe, or why they want to do it.
If you could crack your weapons in the first place, then that would be really nice.
Okay, we could shut them off from afar, but let's say that we can't do that. That would be great. There are such safeguards in every device that's made.
Could you close off all borders?
Aha, we're getting somewhere. You could close off your borders and say, but this gets to this very difficult, how exactly we do that with all these false positives, and we could just keep, now that's the Trump solution, we just keep everybody out, generalizing non-Muslims to everybody.
So they're not allowed ladders. They're not allowed ladders.
Right, can't climb the wall. All right, keep thinking, because there are some,
You could offer a lot of money.
ah,
You try.
who are you going to offer the money to?
You could say if you bring us the weapon, we give you money.
Ah, now we're getting it. So offer a lot of money. Now, how would you go about? Do you post on Facebook? I have $1 billion. So how do you do that?
Have you seen The Night Watchman?
I haven't. So what do they do?
You create some kind of slightly dodgy front shell company on some unregistered island, and you pretend that they're actually
a beautiful woman.
That's according to his thing. That's what you do if you are the Prime Minister of the United Kingdom.
No, so actually, now let's just take Edmund and Steve's and other ideas, and I have met people whose apparently their job was to take large trash bags full of cash and to go and wander the wilder lands around Russia and in Russia and offer to pay anybody any amount of money if they would sell us anything like one of these things. So you flood the market with buyers. And it turns out, if you think about it mathematically, there should be, we hope, very few real buyers. And so the only place we can get purchase on the problem is to have many more buyers, all of whom are on our side, and go out and buy up everything that might be floating around out there. And this is actually the approach that has been followed a lot. Okay? So we like to prevent it.
But won't it just result in enabling the adversary? Like,
In what way?
I mean, if an operation wants to steal weapons, let's give them money is not a great idea.
If we have enough, so there's a math problem to be solved. How much do we offer? Right? And parenthetically, because I was reading up for this and I was kind of shocked, there's this really interesting material called, perhaps someone can tell me, red something. What is it? What is it?
Red mercury.
Red mercury. Red mercury is a mythical substance which there are buyers all over the world trying to buy red mercury because it can do amazing destructive things. And I'll just leave you to read about it. It's very interesting. Okay, so, but getting to, let me watch the clock. Okay, I'm going to move faster. So, after this, what would happen and what can the physics community offer? So, what would happen next? This is an interesting question. So, you're a scientist sitting, at a national lab with some nuclear assay equipment, and you're trying to anticipate. You just heard that this happened. What kinds of questions are you going to be asked? This is my favorite. Mull it over for a moment. So, what will you be asked? A lot of it is obvious, so just throw it out.
So, but what point has the weapon exploded?
We've heard that something happened in Cincinnati. So I'm leading that, right? So that's all I know.
It's only Cincinnati.
Cincinnati's very convenient, because I'm not going to say that because we're being filmed. So you've heard something happen in Cincinnati. What kinds of questions are going to be asked?
Is it nuclear?
Is it nuclear? Right. What else?
How many people have died?
How many people have died?
Am I at risk personally?
Right. Am I at risk? What else?
Has anybody contacted you?
Has anyone claimed it?
Claimed it? Threatened that there's more?
This is the question
key
that
question is,
I engaged in this, in your seat a few years ago, and the question that I just didn't cross my mind at all is, will there be another? And this is actually the thing that seemed to drive the politicians to the ends of their wits the most. Will there be another? And if so, what can we say about it? And so any others?
Why Cincinnati?
Yeah, why did it happen there? Right. Okay, so I abstracted out before you said these things a few of the questions. What just happened? Will there be another one? Who did it? And, there's lots of versions of this. So these are the kinds of questions that are critical to try to get a handle on. Where might this weapon have come from? Is another question. And there are lots of different answers here. It might have been intentionally smuggled in by another country, maybe a known adversary. Maybe it was lost by a peer state and used by a terrorist organization. I've talked about that scenario a little bit. Maybe it was built by a rogue state with a covert program, one that we don't know about or that we don't know much about. Maybe it was built actually by terrorists using materials obtained in some way from a nuclear weapons state. Or maybe it was sold straight up for the cash by a nuclear weapons state to a third party. Or maybe it was diverted from the inventory of a collapsing nuclear weapons state. It turns out these kinds of questions may have answers in technical grounds. There are reasons to, if you stare at those and you think about what underlays each of these questions, you can come up with things that you might learn from basically studying the information available to distinguish these, and I'll tell you a little bit about that. Okay, so 4 hours after the detonation, I'm going to go through this. Terrible things happen. Okay. But I do want to point out, I remember why I put this up here. So there's this fallout cloud that's starting to happen. Can anybody who's not, any of the undergraduates, what is this fallout? What is that? You guys thought about it? What is fallout? Yeah, it's not mysterious. Go ahead.
Dispersed radioactive matter, basically.
Dispersed radioactive material. Okay, how did it get, be more specific. Good. That's right.
The bomb exploded into it spreads it out into the air, essentially.
Right. So at what temperature does the bomb explode? Don't tell me a number of degrees. What is something that we all know that has a temperature similar to a bomb? The sun, right? Big nuclear reactor. So the stuff's at the temperature of the sun. Now, if you imagine you take all the material, you heat it up to whatever that is, millions of degrees, and what happens next to it? What happens next? To a good large amount of it. Think of yourself sitting out by the Thames or the Isis, whatever you call it, on a hot summer day enjoying a cold glass of water. So what happens to this?
It's straight up into the air.
It's up in the air, and then where does it end up? Where, in the very short term, it goes up in the air. It's very hot. Where do you look for it if you're going to go look for it? You look in the air. Okay, well, I'll give you that.
Does it rain out?
It can rain out. It can nucleate around dust and other materials and fall to the ground. But there's one other way that it would come out. You're on the Thames. It's a hot day. You have a cold glass of water. Right, it condenses. It condenses out because it's millions of degrees and everything around is relatively cool. So the challenge is to take advantage of the three processes you just described. Some of it is up in the air, floating around. If you want to sample that, you basically have to fly through it. So you'd like to have something that allow you to fly through the cloud and collect samples. Okay, that's one piece of technical information. The second is it's going to rain out or fall out around dust or water. That means you need to be downwind and looking on the ground, right? That's easy to do relatively because you're not flying through it and you're not in the crater, right? So that's where the most of the information comes from early. And then the condensate that comes out everywhere is mostly close to where the explosion happened, and that's where a great deal of information is. So you'd like to get close, and you'd like to scoop up stuff that's been condensed out on all the materials around. With me? Okay, so now you're a terrorist. With that information in mind, and you're trying to minimize your detection possibilities, under what, how would you choose the target and the timing to reduce all those things from working?
Windy day.
Windy day. That's yep. What else about the day? That's right.
Vacation period. Vacation period.
What does that mean, location period?
Well, any holiday when all of the services which are responsible for detecting.
Right. Maybe a weekend or something, or at night.
Yeah.
That's right. There's a third thing you can do that really is very challenging for the authorities.
Is it do it on a busy day so that saving the survivors first before they start?
That's a little more political. Let's stick with these three physical mechanisms. That's right. But let's stick with the physical mechanism.
Well, you want it to be windy, but you probably also want it to rain and wash away.
Exactly.
Into a river.
If it's a rainy day, the challenge to the authorities is tremendous because all the best information is disappearing much faster than any other. So, I just want you to kind of think about these problems from first principles without getting too caught up in it. And, it's interesting. I think it's interesting. And then, if you choose a career in this area, there are certainly things you can do to mitigate all of these decisions on the basis of that your adversary might have made. Okay, so the local samples, let's go back up at the top. So what was it? Was it a nuclear explosion? This is something that can be answered from space in almost all circumstances. We have circulating, orbiting around the Earth. We have satellites that are purpose-built to look for signatures, to enforce the Non-Proliferation Treaty, to enforce the non-test treaties and the various things like that. These are national assets. I can't say more because I don't know more, but one imagines that a lot of different countries have a lot of different things up there watching. It's not very hard to do. And so that gives you some prompt information. It is not known to me how prompt. An interesting thing is that when the GPS satellites were deployed, there are a couple of dozen flying around. You always have a couple or three, in view. When they were deployed, they all have nuclear sense detectors on them to look for nuclear explosions. So this was done ahead of time to maximize our view. And that data is visible to everybody. So this is a shared data kind of thing, so that everybody can be aware together of what is known and not have it be privileged information. How sensitive these methods are, how accurate, how quick the response, that's information that's generally classified, varies by country. But it's certainly true that most countries in the world will be depending on announcements to come out from those who have technology to say whether it was or wasn't a nuclear or atomic explosion. The next time scale that you get are from the local samples and the fallout sampling. So this takes a little longer. It gives you more detailed information. You can look for specific signatures so that you can maybe begin to distinguish between whether it was a uranium weapon, plutonium, was there any 14 MeV neutrons, which means there could have been a boosted weapon. All this stuff can come out a little later, but this requires readiness. Earth is very large, And if you want to have something which can go and safely, or even under any circumstances, go get samples from the crater area where the condensate was, or from the air as it dissipates, you have to have tools and technology that you can deploy. So my last, I think, question and answer here is, what event happened in the last 5 years that gives you an idea of what our capabilities are as a race for looking at radiation releases like this? Fukushima. So I watched very closely, with an interest in this, to see what the response to Fukushima was. Fukushima happened on March 11th. This information came from the National Nuclear Security Administration, appeared on the web. These were data. This is the east coast of Japan. And this map was created on March 22nd. It came from an American source. You know, this pathway, so there's less than a certain amount of radiation starting at this airport and flying along here. It's pretty clear what they were doing. They were flying an airplane around. I mean, this is my supposition. I don't actually know. It's pretty clear to me they were flying an airplane around, and it's pretty clear that it took 10 or 11 days to get the airplane from wherever it was, presumably in the United States, over to Japan. It's pretty clear Japan didn't have one, right? So you can look at the Fukushima incident and learn quite a lot about what our national technical means are and what is shared. And so I just wanted to point that out, and you can do with it as you will. So the answers really need to be shared quickly to prevent even worse outcomes. You know, false attribution would be terrible. But some people, some institutions, some countries are not going to wish to reveal what they know because they don't want to be wrong. They don't want to reveal that their deterrent posture, which they've said will determine with certainty exactly who did it and why, under any circumstances, was all fluff and bluff. Or maybe they do know how to do that, and they have other reasons. You know, you can think about the game theory aspects of why you would or wouldn't want to share this information. But one of the things that's most critical is that we move to a place through whatever agreements can be forged among countries to know what it is we will and can share ahead of time, so that when the unthinkable happens, we'll know what kind of information may or may not be available, right? And so there's a whole bunch coming, and the time is running out. So what I want to say here is, I'm going to show you the other slides. We'll do a couple, and then we'll maybe shift gears. So this global information, you know, what would other countries know?
You have about 10 or 15 minutes.
Yeah, there's like 25 slides left.
Yeah.
So I have to pace myself. So there's all kinds of global information that will be very important, and the issues that have been raised by this classified report, by this unclassified report, by the classified reports, and by others have led to, let me just say what happened after we did this study. What happened after we did this study is a large investment in the kinds of technical means. A new office was established. There were people hired to begin to do a better job. Maybe there were more planes bought or more remote testing kits. I don't know. But there was a lot of money invested in the technical side. We also called for the equivalent, it's not a war, but the equivalent of war game exercises involving the very top people in government. Because it became very clear that the failure to understand the quality and the nature of information that could be available at any moment and could be coming from other parties around the world who may also be able to see what's going on as well as you can, and could change the way you deal with the situation, needed to be appreciated not by the scientists squirreled away in the lab, but by the people who would be making those decisions. And I'm real happy to say there have been now several rounds of war games, we don't call them that, they don't call them that, but tests, you know, exercises is what it's called, where without warning, the principals at the various agencies are told, okay, this has happened, and they have to get out of bed and go see how they would respond and find out what kind of information would be available, and then the whole thing rolls out. And this has been incredibly, we think, one thing, it's valuable, because it's instructing people on what is and isn't knowable on what timescales. So, you'd like You probably already read those while I was talking. The point is, any attribution, if it can happen at all, would probably be very slow, and retribution would be demanded, from immediately until something. The technology is evolving, but it requires a real investment in both the people to do it, and the kind of careers that are available here are not necessarily full-time careers in doing this. There's not enough work. What you need is a lot of people who know how to do a lot of parts of this, and who would be willing to chip in the event of emergency. So there are many parts of the physics world, around the world, where you could signal an interest in contributing to this area of research and even response, and be taken seriously. So it's a kind of neat thing to know that there's a lot of people listening for young people who want to be a part of solving these problems. They're easy to find. And yeah, the gaming exercises I mentioned. So here's some timescales that are within an hour. You could say whether the event was a nuclear explosion or something else, unless maybe the explosion happened, deep in a basement where maybe that satellite type information couldn't be easily brought to bear. But for the most part, within an hour, you would know that part. Within a day or so, you could probably say whether it was a plutonium weapon or a uranium weapon, that kind of thing. Within a few weeks, you could probably even infer the nature of the device, and therefore probably begin to understand where it could or could not have been made. So there are different designs, and they have different technical footprints. It would take a few weeks. But this is all if...
How do you tell whether it's uranium or plutonium?
You can look at the available decay products, right. You can also get efficiency estimates from the original information from satellite means, and then later isotopic signatures. You can tell a lot. But these timescales are the most optimistic. Well, I'm not in a position to know the most optimistic. These are the are certainly would not be plausible timescales if the teams that need to go to the crater, to the air, to the land nearby to collect all this information don't have access because of all the chaos. So that's just to keep in mind. And so we've already talked about the Fukushima. And if you haven't studied this and you want to write a research paper on a global response or national response to a nuclear emergency, this is a fascinating thing. It's just keeps on, it's a lot to study there. Okay, so deterrence, let's move very quickly, and I just want to say, to understand deterrence, you have to think about, who thinks what are their motivations, where are the numbers greater or lesser for various parts, as we were talking about earlier, and, do these, we call them actors, believe that the U.S. or the international community's attribution capability is enough to lead to action against them? These are the fundamental questions. But let's break it down a little bit. There's 4 different categories of people who might be deterred, and I think that's an interesting thing. And these 4 groups are the terrorist group itself, the ones who actually plan and execute the attack. They may have one set of parameters that describe who they are. Second would be the specialists, who may not be in the terrorist group, but who cooperate, maybe for money, maybe unwittingly, but you have to have some special information, some special skills to carry out something like this. After all, in the 40s, it took the greater part of the scientific community in the world to do these things. The third, there might be a supplier state, supplying meaning here the special nuclear material, the fissile material, or maybe a weapon. And fourth, intermediaries for funding, transport cover, and as I indicated before, this 4th one is where you flood the market and try to use economics to flush out the adversaries. But let's look at each of the 4 real quick. So deterring the terrorist group, they may not care. We have the phenomenon today of suicide bombers, and so let's stipulate that there are people who maybe don't care if they're caught, if they're going to engage in something like this. What other kinds of deterrent what other things might be led? Well, maybe the terrorist group leaders, maybe they don't want the entire organization to disappear from the face of the earth, so maybe there's some risk-averse members of the terrorist group because they want to continue whatever it is they're interested in the long term. Intercepting and tracing the nuclear material to its source may jeopardize whoever first generated it, but it may also impact the terrorist organization itself. And so effective forensics on these intercepts may therefore keep something from happening in the future. But to make that happen, and I don't have time to go into this at length, this is an area where international cooperation and standards is absolutely paramount. Standards means databases so that we can take special nuclear material that's produced from uranium in the United States and from reactors in the United States and all the other countries in the world and put it all in a database so that you can say, oh, our special nuclear material has in it a little bit of manganese or something. And then later, if that trace material is seen, everybody can say, oh, well, we don't think it came from South Africa because they don't have manganese, and the U.S. does, right? And that would be information you share ahead of time rather than waiting until the stakes are very high. And these databases, many countries have such databases. The key is to get everybody to share. And cryptography comes into this. There's all sorts of ways to share now without revealing now trade and commercial secrets so that the information would be available later if needed, but for now it would remain, commercially protected. So there's lots of interesting things to think about there, both for mathematicians and algorithm people and all that. So lots of work has been done there. The specialist is a very interesting group. You need people who know certain kinds of engineering, how to machine these exotic metals into specific shapes, scientists, and there aren't so many of these people. This is a much smaller group of people in the world than many other parts of the chain. And so maybe such people really don't want to be identified as having participated, and they realize that instead of 6 billion candidates for whatever is being fleshed out, maybe there's only 1,000 people who have that information. So they are going to be maybe more deterrable because they are relatively fewer in number and therefore easily tracked down. And these forensics arguments really augment this threat because if you can work out design origin, where the material came from, which plants it was processed in, which reactors it's been in, then you really are putting the finger on some specialists who may have been involved. And so beefing up your technology here is potentially very beneficial to your task, right? So deterrence is different for different groups. When you come to states, every state that has nuclear weapon material, and that is more than just the nuclear weapon states, there are all these little research reactors which have highly enriched uranium in them, trigger reactors and things like that. All the states are responsible for securing it. Those are the rules of the road. And so these states are subject to incentives of all kinds to participate and make sure that they're not the ones either to actually supply somebody with nefarious purposes any materials that they would need, or to be perceived as possibly being the one who supplied it. I mean, those are both terrible outcomes if you're on the receiving end of the retribution, right? So here, a strong attribution capability built on forensics and intelligence and so forth really increases the risks of having a country cooperate with terrorists, poorly formed sentence, or having negligent kinds of practices in their supply chain for their reactors or whatever it is they are doing scientifically. And it's difficult so here we come to the edge of national technical means. A lot of countries have a lot of very specific ways to say specific things are happening or not, and it's very difficult for even close partners to know exactly how effective the detailed nuclear forensics can be, and that's because this is an area where maybe it enhances the deterrent power. So maybe it didn't enhance with other actors, but here with states, it could be very much to your advantage to fluff and bluff. Finally, these intermediaries, they have to be engaged probably and providing money, materials, safe space to work, instrumentation, transport across these borders, all kinds of things written there. And some such people would be in it for the money and some out of conviction, identification with the cause. But the the main deterrent here is not nuclear forensics. The main deterrent here is getting out there, flooding the market, listening closely, infiltrating organizations, and finding out what you know. So, so that's just the kind of discussion. I think I'm going to leave this slide. There's several more slides, but this is what I have is more slides that go into these 4 tasks. But I think these are the 4 urgent tasks that would need to be executed in the event of a detonation. You know, your first task is to be able to say with whatever conviction you can that there is or is not a likelihood of another. Because, you know, if things are bad with one, they'll be much worse with multiple. And so you'd really like to have the answer to that question as much as possible. And if it's a handmade device, it's much less likely to be multiple than if it's been delivered by a state which has hundreds, right? So, you know, there's some basic things you can learn from forensics that might be very, very valuable. You'd like to identify the chain of actors responsible. This is hardly a nuclear forensics task in many ways, but as we said, looking at the looking at the specialists involved and the sources of the material, there are opportunities there. The team on nuclear forensics has to be engaged in response and recovery, whether it's in the United States or not. And the interesting questions there, the forensics teams can tell you some about the risk that your first responders may or may not be facing, right? Because if they can identify it as a non-nuclear dirty bomb, that's a completely different set of risks to first responders than one of the other cases. So this is critical information that comes out. And finally, providing leadership to the public, and not just in the home country or the affected country, but around the world, so that things don't get destabilized. So, you know, I can talk about that in more detail, but let's stop and see if there's any discussion or questions. Yeah.
I wanted to point out that actually the UK has exercised its nuclear forensic capability very recently.
In where?
The limiting of the tell us more.
Well, as I understand it, there was a fellow called Vignetko who was not well liked by. Did I say that? I didn't say that right, did I?
Yeah,
did I say the word right? Yeah. The name right. Okay. Who was not liked by certain people enough that they felt that it would be a good idea to poison him.
But they didn't use just arsenic, did they?
No, they used polonium. And the only point in saying that is that it did exercise a great deal of the UK capability in that regard. And the other point to say is that what was really stressed in that work was that the forensics had to be able to be relied on in court as evidence.
Yes, so there's evidentiary standard.
Yes, and that made, and I think that for a start it made it very difficult to do it, but it was very important that it had to be done that way, because our retribution in that case was a legal one. And although nothing is yet, the 2 people who have been identified were both Russians, I understand, have not yet come to court. Time will tell eventually.
One of them is head of state, isn't it?
It's a question of time. Eventually it's time. And then evidence has to hold up in 10 or 20 years' time.
So the question of evidentiary admissibility is one that varies by country, but in the U.S., the standards were set for scientific evidentiary rules with pharmaceutical companies and things like, and there's a famous case, I think it's called Daube versus Merrill or something. And essentially, since 2006, 7, 8, when we were working on this through 2000 now and forward, the goal is to share the techniques, to get peer review, and to get standards across laboratories so that it all will be admissible in court to the greatest extent possible. And that means just anyone who's, so this is maybe the people in the back, anyone who's written a code that you can use, and you think, oh, that just took me 5 years, and now you want to make it so that other people can use it, you know, that's 50 more years, person years of work. And it's similar to going from a tool or technique that can give you a piece of information to getting it to be admissible, a technique that leads to admissible evidence in court is a huge lift, and that's been I left those slides out, but that's good, right?
I missed the start, so I don't know if you guessed this at the start. What do you think of the probability of a nuclear weapon and that detonation in a major European capital within the next 5 years?
So my opinion is completely uninformed and so irrelevant. But what I reported at the beginning was there was a series of meetings in the U.S. which were made public, and I have the report on my computer to flip to if anybody wanted to see it. In 2007, there was a report chaired by three folks, William Perry, Ashton Carter, and someone else, and Mike May, who helped me with this work. So Mike May was leader of Livermore Laboratory, if I got that right. At the time, Ashton Carter was an expert on these kinds of issues, and William Perry, I think, was Secretary of Defense at the time. Now, Ashton Carter is Secretary of Defense. So these are people in the know, and they basically recounted to all of us in the audience, they thought it was a greater than 50% chance. So there was a great deal of fear in 10 years ago that such a thing should have already come to pass. It was really quite remarkable.
It's already happened. Or not?
Yeah, it hasn't happened. So surely we're proving the prior wrong, and it must be getting less likely in some abstract space. But it's a terrible thing to contemplate, and there are things you can do to, prepare.
It's because none of these Russian nukes actually work.
People press the button and go on.
We'll come back. Let's do here.
What do we know about what the actual stockpiles are of materials in the world, and what are the mechanisms for?
So the questions. So one thing that has happened is there's a lot of highly enriched uranium, up at the 90% level, in small research reactors on university campuses, for the most part, around the world. And it's unguarded. I mean, it's locked. It's unguarded in the traditional sense. And there's not enough of it, particularly on any one campus, to be a threat, but you could imagine that there's a lot of it. There is a lot. And so one of the things that has happened in the last 10 or 15 years, maybe more, is there's been a dedicated effort. So all that stuff was part of the Eisenhower Atoms for Peace, where we share nuclear technology around the world so that people don't feel the need to develop their own tools and techniques and become nuclear weapon states. And so there are, literally dozens of countries who have this sort of low-level stuff. Well, one of the things that has happened in the last 10 or 20 years is to try to buy it all back and to bring it back to, U.S. is one major party, but I think it's mainly to nuclear weapon states, and get it away from just the general sort of out there. So an enormous amount of progress has been made on that. There's still more to do. The next big chunk of stuff that had everybody worried was in Ukraine. There were a lot of forward-based missiles and weapons of various kinds in Ukraine. And the understanding I have is that was all removed well before the Crimean stuff. That was all brought back to Russia and secured. And so that was an enormous push that involved many countries around the world and seems to have been successful. And then then you go down the list to the next chunk and the next chunk. And I think that roughly every 8 years, everybody says, oh, we got to do more, and there's another push, and the next item on the list gets some serious attention. And then, funding is tight, and progress is made, but it's not a continuous process. It's kind of a step function. It's my impression.
All right.
There was two more, one in the back.
Guys, we got it.
Is it dinner?
Unfortunately, we have to stop. Thank you, Bill, for this fantastic lecture, and we'll continue talking.
Cheers.